I'm Bethany Lusch, and I work at the Argonne Leadership Computing Facility. My background is applied math, and I work on machine learning. And I'm going to talk to you about optimization methods for machine learning, which you can think of as kind of the math underneath machine learning. So what do I mean by optimization? I mean we want to minimize some function f. X would be the part that we can control. In optimization, you would often call the function f the objective, but in machine learning, we might call it something like the loss. And you could have constraints. And whenever you're thinking about finding the best of something, that's probably an optimization problem. So for example, finding the best route, you could think of as minimize the cost of delivery subject to all of the mail gets delivered. And it's standard to write problems as minimization, but of course you could be maximizing. And you could always, if you want to write it as a minimization problem, put minimize times -1 times your objectives. So for example, if you want to maximize profit, you could write it as minimize negative profit. So finding the best product could be minimize negative product subject to safety. And you don't need constraints, of course. So you could be looking for, say, like your best prediction model by minimizing prediction error. So those are some like general optimization examples. But underneath most machine learning problems, you have an optimization problem. So the best prediction model could be a machine learning problem. Or if you're trying to find the best recommendation, you could think of that as something like minimize the number of people who don't buy something when they visit your website. Or if you're thinking about a clustering problem, the best clusters you could formulate as minimize the distance within the clusters while maximizing the distance between clusters. So I'm going to talk about some general kinds of optimization. And to be more precise, you could think of minimizing a function f0 of x with some constraints. Fi of x is less than or equal to bi. And you don't have to have less than or equal to constraints. This really encapsulates also greater than or equal to or equality. And here I listed some big categories of optimization in order of like how hard it is, so kind of how desperate you are when you're in this category. And I'll go into those categories. But kind of roughly, if you're in those easier categories, you might spend more of your time on formulating your problem to fit that category so that you can use the easy optimization algorithms. And if you're more towards the bottom, you're stuck with some harder optimization problems. So maybe you're spending more time on the optimization itself. So first example would be that you have a linear optimization problem, and for historical reasons, this is often called linear programming. So you have you're optimizing a linear function, and you have linear constraints. You may have seen the phrase convex polytope, and I have an example drawn here in yellow. So it's like you have a region constrained by lines here, or more generally hyperplanes. And here, the red line you could think of as your objective function. So if you think of like level sets or kind of changing the intercept, you could move the line along and try to minimize where the line is, restricted to this region. So if you can write your problem as a linear program, there are great polynomial time algorithms for this. And local minima are global optima, so that's great. So if you think about calculus, when we want to find critical points by setting the derivative is equal to 0, that doesn't mean that it's necessarily a minimum, and it definitely doesn't mean it's a global minimum. But here in linear programming, local minima are global optima. Okay, next level would be quadratic programming. So you have a quadratic objective function, and the constraints are still a convex polytope. So here I again have drawn in a convex polytope and some level sets of a quadratic function. And so you would want to find the lowest point in the level sets that's still within this region. And if Q is positive definite, which has to do with eigenvalues, then you have a convex problem, which means that there are weakly polynomial time algorithms for your problem, and you still have that local minima are global optima. So you can take advantage of any algorithms that are good for quadratic programming. Next level will be convex optimization, so a little bit more general. You have a convex function that you're optimizing over, and you're restricted to a convex set. And if I drew in some example convex functions. If you're not familiar with that, it's like you draw a line segment between 2 points on your function, and the segment should be above the curve. So you can think of like x squared. In some cases, you still have a polynomial time algorithm. The great thing is that you still have that local minima or global optima. And this isn't as perfectly developed, but there are reliable methods that are specifically good for convex optimization. Okay, so here I drew an example of a non-convex function. So we have multiple local minima. But in this category, let's say it's at least differentiable. So we're assuming we have a differentiable objective function. In general, these problems are NP hard. But at least if you have gradients, you can take advantage of that and use algorithms that use gradients. It's even better if you can do second derivatives and you have Hessians. So for example, we learned about the tau package earlier this week, and they specialize in this category. Okay, and then what if you don't even have differentiability? Well, that is definitely generally NP hard. It could be arbitrarily impossible. So here I drew a ridiculous function that's just random, but there you can hopefully see that there's one point that's much smaller. So if you don't know anything about the structure of your function, you're only going to be able to minimize it if you just are totally lucky. So hopefully you at least have some structure. And there can be specialized algorithms. And we could think of general optimization as being either continuous optimization or discrete optimization. Continuous meaning you're optimizing over some continuous region, like in real numbers. And discrete meaning you're optimizing over discrete space, for example, sets, or you require integer solutions. And largely, these are totally different methods, but there's a little bridge there because there's some overlap, especially if you relax your discrete problem to be a continuous problem. And both types show up in machine learning. So to get back to machine learning, let's say, for example, that you have documents, X, and you want to label them as being related to politics or not. So label 1 or -1. This is a problem where it'd be hard to come up with rules by hand to code into your program, so you might want to use machine learning to learn some function h to go from the document X to its label. Now, what we would really like to do is minimize the expected risk of misclassification. So search over function space, find the best h possible. And we'll go into why we can't exactly do that. But some common issues are, how do we pick this family of functions h, because we can't really optimize over all possible functions? And how do we know which function h is optimal? Okay, so I mentioned really we would want to minimize the expected risk of misclassification over all possible data, but we don't know the probability distribution of all possible documents. So really, we minimize the empirical risk, so the error summed over the data we actually have. And the way I wrote it here, the penalty is 0 if you classify it correctly, and 1 if you're wrong. That's like a discrete formulation, and that's hard. So usually we would instead use some other loss function, which I called L here, that's maybe smooth or something. And another thing we might want to do is search over a class of functions h that are parameterized, so then we could say we're minimizing over the parameters. Okay, so some big themes in machine learning. One is overfitting versus underfitting, which I'll go into a little bit more. But on the one hand, you want to pick a family of functions where it's possible to get a low error on your training data. And on the other hand, you also don't want a big gap between that theoretical expected risk and your empirical risk on your actual data. So this idea of really we want to be able to generalize. So you could call this bias versus variance or overfitting versus underfitting, and I have more on the next slide about that. But also when you're picking a family of functions to optimize over, you want to make the optimization problem easy. So you might want to pick a convenient representation of the functions, and you might want something like smoothness. So more about bias versus variance. On here I have some blue data points. And on the left, I have this like crazy function, but it fits this data perfectly. But it's not really learning the pattern here. So we would call that overfitting, or some people would say high variance. And then in the middle, it's like, well, what if we just fit a line? Well, a line is not expressive enough to really get the pattern here. So you're going to have a really high error. So you'd say that like linear regression is too biased for this problem, or underfitting. And something balanced for this data could be fitting a quadratic function. Okay, so back to these categories of optimization, but with some machine learning examples. If you think about linear regression, the least squares version, you could write down the objective like this. So just fitting a line to your data. And if you multiply it out, you might see it looks like a quadratic program. So that gives you some idea of why linear regression is generally easy. Okay, one machine learning algorithm is called support vector machines. I'm just going to talk about it briefly. Here in this picture, we have two types of points, blue and red. And we want to find a linear classifier that separates blue from red. But there's a lot of lines you could draw between blue and red here. So support vector machines try to find the one kind of in the middle, which helps you generalize more. So the one with the biggest margin from the nearest points. So the kind of trying to show that with these dotted lines. So that kind of gives you some flex room for future data sets, for future data. Okay, and then you could write down, I'm not going to go into the details, but you could write down the subjective function like this big mess. And if you read up on it, it'll eventually make sense, but it is a quadratic program. So that gives you some idea of why the algorithm for support vector machine is relatively good. And I want to mention that more generally, you could have a kernel support vector machine that can do nonlinear classification, so you don't have to pick just a line to separate, and that's still a quadratic program. Another common machine learning algorithm is k-means clustering. So maybe you have this data here on the left, and you want to find groups in it. You could think of this as finding a clustering that minimizes the distance within each cluster. And if you write down the k-means objective function, I have it here. We're summing over the clusters and summing over the points in the clusters. And we want them to not be very far from their centers. And this is an NP-hard problem, and it's a discrete problem. And so when we do k-means, we're actually doing an approximation algorithm. Okay, so today we're hearing a lot about deep learning. I just drew a tiny little network here. We have input x. We have the network is a function f. We want to minimize the error. This is generally non-convex. So we have to go a level below that. And really, usually in deep learning, it's too hard to compute second derivatives. So we have to go to the next level. Okay, we can compute gradients with back propagation. So that's good. But it's pretty far down this list. We're fairly desperate. And we want to scale, so we use gradient descent. But yeah, it's non-convex. We're going to have a lot of issues with local minima. Okay, so before I said roughly when you're in the upper part, you spend more time on formulating your problem to be in this category, and roughly in the lower part, you spend more time with your difficult optimization problem. So sort of analogously for machine learning, if you want to use some of these like nice machine learning algorithms, you might spend more time getting your data in a form that works well for these methods that are relatively biased in the sense that they can't necessarily express a really complicated function. So you might spend more time like choosing good features for your data and that kind of thing. And roughly in these lower cases, you maybe don't have to mess with your data quite as much, but the optimization is difficult. So just like a rough generalization. Okay, and I mentioned before that two themes in machine learning is this bias versus variance, or overfitting versus underfitting, and wanting to be able to efficiently solve the optimization problem. So specifically for deep learning, you have a lot of control over the overfitting versus underfitting spectrum. And big neural networks can be very expressive, so they can handle like really complicated patterns in your data, so it's like low bias. But that also means it's really easy to overfit. On the other hand, it means generally you can spend less time getting your data into like some great feature representation, because the deep learning hopefully can kind of learn some good features. On the other hand, the optimization for deep learning is tricky. It's a lot of times it stalls out, or you get stuck in like a local minimum or a saddle point. Okay, so I think you've seen this before, but to talk a little bit more detail about gradient descent, we want to minimize some function f. The thing we can control is w, and we're going to take steps forward iteratively. So in this picture, we have some initial weight, and we take a step in the direction of steepest descent, the gradient. And you keep doing this over and over for some distance in that direction, and the alpha is how far you step. Okay, so let's say we write down our objective function as summing over the errors on each data point. Then batch gradient descent means that you use your whole data set every time you compute a gradient. And stochastic gradient descent technically means you only use one data point for every step. And mini batch gradient descent sort of in between. You use some subset of your data to calculate each step. So if you do batch gradient descent, every step's pretty accurately going in the right direction, but it's expensive to compute. Stochastic gradient descent, where you only use one random data point for each step, is pretty noisy, but it's really fast to compute. And then mini batch gradient descent is really common. It seems to be some kind of happy medium. But as a warning, people hardly ever explicitly say mini batch gradient descent. A lot of people say stochastic gradient descent when they really mean mini batches, including me. And when we talk about the hyperparameter batch size, that's, I guess maybe you'd want to really say mini batch size. Okay. So here are some crazy pictures about what maybe your loss landscape looks like. So this F that you're trying to optimize over. And really it's hard to visualize because really we're in some huge dimensional space. But this kind of gives you this idea that, okay, we have something really non-convex and it's kind of dangerous to just head downhill. One consideration is your step size alpha, so how far do you go in the direction of your gradient. If you step too far, you could overshoot, and your gradient isn't actually valid that far. If you step too small, you're moving really slowly and you're kind of committed to this particular downward direction that you're on. So like a positive of bigger steps is that maybe you kind of jump over to another region. You also have to be really careful about initialization. So you can see from this picture that depending on where you start, you could be pretty unlucky and just heading downhill. And maybe you can make the whole problem easier. So this paper argues that skip connections, which I'm not going to go into, make the surface look way better, like on the right. And more generally, there could be some tricks that you do in deep learning to try to just make this all easier. Okay, so in practice, we don't usually literally use gradient descent. We use some variance. If you look at these deep learning libraries, you have a lot to choose from. Really popular right now is the Atom Optimizer. One feature is that it learns a separate learning rate for each weight. It also has this idea of momentum, so using this moving average of the gradient. And it uses squared gradients. And if you go to this link later, there's a cool visualization of why momentum works. Okay, so overall we have this issue of underfitting versus overfitting, and regularization is a common way to try to avoid overfitting, and L2 regularization in particular is very common, especially for deep learning. So here we're minimizing the error like normal, but we added on another term. So this is the sum of squared weights. And we have this hyperparameter lambda to balance these two. So roughly, if we make lambda big, then it discourages large weights. And this somehow helps avoid overfitting. So some idea that these like big coefficients lead to high variance, and then really overfitting your data. And there's a lot of other ways to do regularization, but this is the most common one. Okay, so a general caution in optimizing your neural network or machine learning in general is it's really easy to overfit. One question is, can you generalize outside of your training set to your validation and test set? So that's what is standard to check. But something that's really tricky to think about is being able to interpolate to data that you haven't collected. So if your data you collected isn't a perfect match for the distribution of data that you'll see later. And then extrapolation is extra difficult, especially with neural networks. You're really only learning a function on this domain that you're training on. So to summarize, we have these different kinds of optimization that get kind of increasingly difficult, and you have less convenient methods to use. And some big themes to always remember in machine learning is this trade-off between overfitting and underfitting, and that you're trying to set up your problems so that you can do the optimization efficiently. And if you want to go more in depth mathematically, there's this recent review paper on optimization methods for large-scale machine learning. It's something like 88 pages long, and a lot of it's about variance of gradient descent. All right, that's it. Any questions?
What's a skip connection?
Oh, yes. Well, you can think of it as data from one layer going directly to a later layer, kind of skipping the intermediate layers. But you can also think of it as a layer being like a function of the last layer plus some data from earlier layers. So for example, you could do, let's say your input data is x. The output would normally be f of x, but it could be x plus f of x. So it's kind of like you're letting the input skip all the way to the output. And if you search residual networks, you can learn more about that. Yes?
Think a bit more on the hashing of the general and same multi-layer neural network. How does that look like the hashing?
Oh, how does the Hessian look for neural networks?
How is it easy to approximate with sort of a relatively simplistic mix?
I think it's logistically easy, but just computationally expensive. Does anyone else have experience with that? And I think like places like TensorFlow let you call a function, and it just takes a long time, so it's generally considered not worth it, but some people are exploring that. Yes.
Can you tell me what is done in terms of changing the learning rates through the training?
So the most basic version would be just keep alpha the same. But people are definitely finding improvements by having like some kind of schedule for the learning rate, or you could think of Atom as kind of automatically doing that. And some people have heuristics like, if the optimization starts to slow down, this is what you should do to the learning rate. You're kind of plateauing, so let's mess with it. Does that kind of answer your question? Yes?
Are there ever any issues with like a floating point round up when trying to estimate these rates? Like if they were smaller?
Let's see. I think in my experience the data is too noisy for like float 32 to matter, but I mean people are experimenting with lower precision and when you can get away with that. Because then you could have a speed up if you could get away with incurring that rounding error. Sarah?
So when you're working with gradient descent and you potentially have a lot of local minimum, how do you sort of characterize the sensitivity to your starting points, or like those sorts of things that could lead you to different local?
Do you mean in some sophisticated way, or I guess people have carefully looked at like schemes for initialization. Sometimes they have a little bit of theory behind it, and sometimes not. And those are like things you can change in places like TensorFlow. And in my experience, that can matter a lot. And even just running your code 20 times or something, you might get a much better result because the random initialization was better. Does that kind of what you're getting at?
Yeah, so I think it's, there's not really a standard for trying to go about it.
Well, Elise might be able to talk about, is Elise still in here? I guess if you wanted to like think about it in like a sophisticated way about how your distribution of initial conditions moves forward. But yeah, people are definitely looking at good schemes in practice, and it can say things like, if you scale your data this way and have this kind of activation function, then this kind of initialization is good, and it can really matter a lot. Anyone else? Okay, thank you.